Okay, so in this example, we have air contained in a piston cylinder device, and this air is initially at a volume of 400 liters, a pressure of 150 kilopascals, and a temperature of 300 Kelvin. And this piston cylinder device is such that at the initial state, the piston, which is in blue, is resting on these black stops here. Okay, and what we're going to do is we're going to allow, we're going to allow heat to enter the system or enter our gas, and until the volume of the air inside the piston cylinder assembly doubles. And we're also told that a pressure of 350 kilopascals is required to move the piston. Okay, so we're asked to find the final temperature of the air. We're going to call that T3. I'll show you why in a second. The work to move the piston to the final volume, which is double the initial volume, and the heat transferred during the process. Okay, so I'm going to begin by establishing exactly what my system is. Okay, so in this case, if I can get my tablet to cooperate, in this case, we're going to draw a boundary around just the gas. Okay, so my system does not include the piston, does not include the cylinder, it is just the air. Okay, so if I look at the description of the process on a PV diagram, this is a particularly useful diagram in this case. I kind of get a bit better description, or a bit of a visual description of what is happening to my gas over the course of the few processes that are happening here. So I'm starting at some pressure and volume at state 1. This happens to be 150 kPa and 400 liters. Okay, so I'm going to begin heating the gas, and I'm going to heat the gas at a constant volume until I reach a pressure that is sufficient to lift that piston. And so that happens to be a pressure of 350 kilopascals. So once that piston is off of the stops, the pressure inside my gas doesn't change because the pressure is mandated by the weight of that piston. So no matter how far it moves up and down, the pressure inside is the same because the force that the piston is exerting on the gas is the same. Okay, so I'm going to continue heating at this constant pressure until the piston tops out at a volume that is double my original volume. So when we get to 800 liters, we're going to stop. All right, so then I've got I've labeled each one of these kind of intermediate, or each one of these steps, 1, 2, and 3, 2 sort of being our intermediate step. Okay, so the final temperature T3 is the first thing we're going to tackle. And what I'm going to do here is I'm going to go ahead and begin by writing the ideal gas equation of state as given in lecture. Okay. When you see problems involving ideal gases, it's always a good idea to go ahead and write down this equation because it really gives you a jumping off point for some of the things that you're going to be finding. Okay, so if I rearrange this equation, PV over T equal to M times R, I'm going to note that no matter where I am between 1, 2, and 3, my mass of my air and my ideal gas constant, neither one of those two are changing. Okay, so I know that P1 V1 over T1 is going to equal P3 V3 over T3. So T3 is really what I'm trying to find. So finding T3 should be pretty straightforward here. So it's going to be equal to P3 V3 over P1 V1 times T1. Okay, so notice this fraction here is dimensionless, so my T1 is going to mandate what units T3 is going to pop out at. So P3 is going to be 350 kilopascals. V3 is the same as V3 is double V1, so I could really write this as 2V1. P1 is 150 kilopascals, and then again V1. So it wouldn't have hurt to plug in 800 liters and 400 liters, but I don't really need to. And then, of course, T1 is 300K. So that gives us a final temperature T3 of 1400 Kelvin. All right, so that one's done. Now, let's move on to the work to move the piston W13. All right, so all the work that is happening in this system is boundary work. The air is exerting work onto the piston to move it, to expand our system volume. Right? So we always write this boundary work as the integral of pressure times volume. So here we're going from some volume at state 1 to another volume at state 3. All right. So do note that if we look back up at our PV diagram, the volume from 1 to 2 is not changing, so I don't have any work happening in this process step. I've really only got work happening from 2 to 3. So if you wanted to denote your work as W23, that would also be correct. That would be totally fine. All right. So you'll also note that the integral of PdV is just the area under the curve from 2 to 3. So it is simply, let's see if I can kind of shade it here. All right. So it's all this stuff. All right. So if you didn't remember how to perform the integration, you could use simple geometry to figure out what this area is. All right, but we're not going to do that. We're going to note that during this process, so in this case, this is equivalent from V2 to V3 P dV, where this is P2 or P3, however you want to denote that. And we are going to realize that P is constant during the process from state 2 to state 3. So we can pull that out and the integration becomes trivial. So again, V2 is the same as V1. So we could denote that either way, and that would be fine. So we have now 350 kilopascals times V3 minus V2. So we're going from 400 liters to 800 liters. So that difference is 400 liters. And 400 liters, so we'll denote 400 liters like that, and then put out a conversion factor over here because we want that in cubic meters. Okay, so in 100 liters, there is 0.1 cubic meters. Okay. So here, that gives us 140 kilojoules. Now, just a quick note on units. If I had used pascals for my pressure, then my final answer would have been in joules. But because I've used kilopascals, then my final answer is in kilojoules. Okay. So, work is done. So now it's time to look at the heat transferred from state 1 all the way to state 3. Right, so Q13 is what I'm looking for. And before I get there, I'm going to need to consider an energy balance on my gas. All right, so let's go ahead and consider the change in energy of my system from 1 to 3. So that'll be delta KE 13 plus delta PE 13 plus delta U 13, and that's of course equal to Q13, which is what I'm looking for, minus W13. Okay. So because I've only used my gas or the air in the piston cylinder assembly as my system, I don't care about changes in potential energy of the air. That is going to be insignificant. And I'm also going to neglect any changes in the kinetic energy of the gas too. I don't expect it to change velocity over the course of this process. So what I'm left with is delta U13 equal to Q13 minus W13. Right? So let's rearrange this equation. Like so. Okay, so now when I break down capital U into capital delta U into M U3 minus U1, it reveals to me that I've got some things that I'm going to need to find. So I'm going to need to find the mass of the air, which was not given, and the specific internal energies at states 3 and state 1. Okay, so let's go about finding mass of the gas first. So again, I'm going to turn to my ideal gas equation of state, and that's going to be PV over RT. And I've got pressures and volumes and temperatures defined at multiple states now. So I could choose state 1, I could choose state 3. It's not really that critical. Let's just choose state 1, because all those are given in the problem statement, so those are easy to retrieve. So here I've got 150 kilopascals, 0.4 cubic meters. That's of course my 400 liters. R, which is 0.287 kilojoules per kilogram Kelvin. And finally T1, which is in 300 Kelvin. When you're using the ideal gas equation of state, make sure you always use absolute temperature. So do not be tempted to put temperature in degrees Celsius into this place. Right? Okay, so that gives me a mass of 0.697 kilograms. All right, so on to U1 and U3. So U1 is going to be the internal energy of my ideal gas at 300 Kelvin, and U3 is going to be, of course, the internal energy, specific internal energy at 1400 Kelvin. And these specific internal energies are only functions of temperature. So I don't care what the pressure of the ideal gas is to determine what its specific internal energy is. All I need to know is the temperature. So there's two ways I could go about this. I could use the constant volume specific heat multiplied times an absolute temperature to find my specific heat values. Or I can use a table. So in this example, we're going to use a table because being familiar with both approaches is important. So for the first one, my gas is at state 1 is at 300 Kelvin. So that is this line here. So I've got 300 Kelvin. So I'm going to come over to my internal energy column, and here that is 214.07. Check my units in the table. Up here at the top it tells me that U is provided in kilojoules per kilogram. So 214.07 kilojoules per kilogram. Alright, so back over to the table. Now I need to find 1400 Kelvin on my table. So do note that your table is split up into kind of two columns, which is separated by the center here. So my temperatures go from 200 up to 440, and then over here again 450 up to 740. So I'm going to scroll down onto the next page if that's possible. Okay, here we go. So here we go, 1400. That's going to give me an internal energy of 1113.52. Okay. So now I'm ready to find my total heat transfer during this process. All right, so minus my value of work. So my value of work was positive up here, right, 140 kilojoules. So minus positive 140 kilojoules. All right, oops, don't need that. Okay, so just a quick sanity check to make sure all my units work out. My work is in kilojoules. My internal energies are in kilojoules per kilogram. So when I multiply through by kilograms, I am left with kilojoules in my first and second terms, which is exactly what I'm looking for. So this gives me a value of heat transfer from 1 to 3 of 767 kilojoules. Okay, so one more thing to note, this has a positive sign. So this tells us that heat is transferred to the system. Okay, this makes sense. We need to give the gas heat so it will expand and move my piston upward and do work against the piston. So if you wound up with a negative quantity for heat transfer, which would tell you that heat was taken from the system, and your piston is moving up, that should ring some alarm bells in your brain and tell you that perhaps you've made a sign error somewhere above. So do continue to do these sanity checks for yourself and make sure that your answers are making physical sense for you. Okay, so with that, I'm done with this example. Thanks for watching.